Problem 21 is another optimization problem. So it's a bit more complicated to set up than some of the other problems we've dealt with, but it gives us some important information off the start. So we have an island, and that is our end destination. We call it the orange dot island. The problem tells us that it is 2 miles off the coast along a straight shoreline. So if this is our shoreline, this island is directly 2 miles off it, just like I have drawn here. So we're staying in a cabin that is 6 miles west of this island. So some 6 miles in this direction. We want to get from this cabin, C, to this island, I. And it gives us two different speeds that we move at. We run at a rate of 8 miles per hour, and we swim at 3 miles per hour. We want to know how far we should run if we're running straight along the shoreline before we should turn and swim directly towards the island. To minimize, which is how you guys know it's an optimization problem, to minimize the time it takes to reach the island. So just like every optimization problem, we have to have some equation that we're going to take the derivative of and set equal to 0 to find the minimum or maximum of that equation. In this case, it's not some like standard surface area equation like we did before, but it's some time equation. So our total time is going to equal the time we spent running plus the time we spent swimming. And so now we need to figure out equations for each of these two time pieces. So we know that distance equals our speed times our time. So our time is going to equal our distance divided by our speed that we're going. If we plug into these equations, we know that our time running is going to be our distance running, which I'll call R, divided by our speed running, which is 8 miles per hour, plus our distance swimming, which I'm going to call S, divided by our speed swimming, which is 3 miles per hour. Now we have an equation with two variables, and we somehow need to relate one of these variables back to and translate it into terms of the first variable so we can take a more simple derivative. So we can do this because we can relate this distance R to this distance S through trigonometry. So we know that this distance swam is going to be the x distance swimming is going to be some fraction of R, of 6 miles, excuse me. So we know that swimming in the x direction equals 6, our total mileage in the x direction, minus whatever distance we ran. And our swimming in the y direction is just going to be 2 miles. So we know our total swimming, per the Pythagorean theorem, is going to be 2 squared plus 6 minus r squared. And we know that S equals the square root of all of that. So now we can plug that in to this equation over here. Once we have that equation, you can now see the only variable we're dealing with is the distance ran. Our next step is to take the derivative of this equation and set it equal to 0. I've gone ahead and taken the derivative of this equation, and then once I did that, I set it equal to 0, which is this step right here. Once you've set it equal to 0, you can then go ahead and solve for r. One thing I want to highlight is I never factored out this 6 minus r squared value. I just continued and took the derivative and did the math with it in there, and that's because it cancels out and makes the problem a little bit easier later on. As you can see as we go, we get left with 6 minus r, and we can then factor out, on both sides of the equation, we can then factor out some of those numbers, and we get a relatively easy equation solving for r right here. This 36 over 55 is a little bit tricky math, so I just left it as a fraction for now, and that's fine. And the last thing we need to decide is when we square both sides, This is a plus or minus, right? So we have 6 plus or minus the square root of 36 over 55. Now, the best way to decide if it's plus or minus is simply to look at our domain. So we have 0 miles right here, and we have a max of 6 miles right here, and at some point in that domain, we have to turn and begin swimming. So logically, it cannot be greater than 6 miles. So our optimal running distance to minimize our travel time equals 6 minus square root of 36 over 55 miles, which is approximately 5.2 miles. And at that 5.2 miles mark, we would turn and start swimming towards the island. Problem 26 is another optimization problem. In this situation, it's asking us to maximize the area of the rectangle that is within this ellipse that they give us. So first off, in every optimization problem, we need to figure out what equation we're optimizing. In this case, it's going to be area. So we're going to find some area equation, and we're going to take the derivative of it and set it to 0 and solve for some variable. So the area of a rectangle is length times width. So we know that we have some length and some width. Some other things that we know that will help us simplify this equation is we know that if we center this ellipse and this box on an XY grid, that the length of the box is going to be double whatever the x coordinate is where the box will meet the ellipse. And the width is going to be double the y coordinate of where it meets on the ellipse. So we know that width is going to equal 2y, and we know that length is going to equal 2x. And we can substitute this into our equation. So now we have area equals 4xy. Now we have to do something about those two variables because when we take the derivative, we only want it in terms of one singular variable. And this is where the constraint that our rectangle is going to be within this ellipse is going to happen. So we have the equation of the ellipse, which is x squared over 4 plus y squared equals 1. We can solve this equation in terms of y to get equal plug into our area equation. So y equals 1 minus x squared over 4 to the 1/2. We get this, and now we can plug this into our original equation. So we get left with our area equals 4x times 1 minus x squared over 4 to the 1/2. And now we're going to try to take the derivative from this step right here. Okay, so I've taken the derivative, I simplified another step or two, and then I took the derivative. And at this point, we're going to set it equal to 0, simplify, and then solve for x. Okay, so we're left with x equals plus or minus square root of 2. We are looking for actual dimensions, so when we plug this in to find width or length, it ends up having to be positive root 2 because we're essentially using the bounds from 0 to 2 to find our dimensions. So we can find the total area of our box by plugging into this original equation, or one of the original equations that we built, with 1 minus x squared over 4 to the 1/2. And this will give us 4 times root 2, 1 minus 2 over 4 to the 1/2. Which gives us 4 times root 2, 1 minus 1/2 to the 1/2, which gives us 4 root 2 times 1/2 to the root 2, which gives us 4 times 1, which equals an area of 4. The last step is to find the dimensions of this box. So we need to find length, which equals 2 times x, and width, which equals 2 times y. And we also know that area equals length times width. So we can go ahead and solve. Length equals 2 times root 2. And then we can solve for width equals area divided by length. So we have width equals 4 divided by 2 root 2, which equals 2 divided by root 2, which we can go ahead and simplify that and get 2 root 2 over 2, which equals root 2. So our final answers are length equals 2 root 2, width equals root 2.